States of matter. Not states that matter, but states of matter. You know, every state matters. But if we take a look at this ice cube, you can see that it is solid. Okay, it has a little shape to it, a little curve to it, right out of my refrigerator, my freezer really. All right, and so it has a certain amount of volume and a certain shape, and it does not change. That's one of the properties of a solid. Okay, here we have a jar of water. It's a liquid. It doesn't have a shape. It has whatever shape its container has. So it's got the shape of my hand while it falls off my hand, whatever. So it doesn't have a certain shape, but it has the same volume always. And then we have gases. Now I don't have a good gas to show you. I have steam coming up from this boiling water. And if you've noticed, all three of these are forms of water, states of matter that are of water. Solid water is called ice. Liquid water is traditionally called water. Some people call water as a gas steam. All right, but you have to be careful because the steam you see right here is actually water in its liquid form in little tiny drops. But the steam that you can't see, okay, water when it's a hot gas, okay, we can call that steam. That is another form of water. Now gases don't have a certain shape and they don't have a certain volume. We can change their shape by putting them in a different container, and we can change their volume by warming them up. Now to some extent, yes, you can change the volume of some things by warming up slightly, as we talked about with density, but for the most part the volume does not change. Okay, what's the difference in the three kind of states of matter? Well, remember, matter is made of atoms, okay, little tiny atoms. Ice is a solid form of water. It's rigid. You smack into it, you can break it or whatever like that. And the reason it's so solid is because all the atoms are packed tightly together in a nice configuration, so they have strong interactions between them, and they don't want to shift position at all. And so they are held rigidly right in one spot. Okay? Now liquids have no particular shape, although there's still some interaction between the molecules. So the shape here is there's no shape because the molecules are only slightly interacting and they're not rigidly held in place. So they can touch each other, move around to be attracted, but not tightly, so they don't get stuck. They can keep moving around each other so they have no particular shape, and it's just any sort of form you want. Gases, I'm taking a liquid water and I'm heating it up to make a gas. All right? Gases are atoms that are only weakly interact with each other, and so they just fly by each other. They might interact strongly, but in the shape, they're moving too fast to get stuck next to each other. So they have no particular shape because they're all bouncing around all over the place. They're very spread apart, typically, right? Much more spread apart than the others, and so they don't really have any shape or volume because they can be spread apart more or less because they're not really interacting with each other nearly as much as when you're in water and we're in liquids and solids. So we've kind of ordered them from cold things to hot things. And if you think about that, remember, heat is a way of adding energy to things to change their temperature. Okay, and the more temperature you have, the higher temperature you have, the higher temperature, the more heat you have, the more energy you have, and so things are moving faster. So things in solids are moving very slowly, thus they're kind of hard. They're not going to move out of the way. Things in water are moving a little bit faster, and liquids moving a little bit faster. They can move out of the way, but if you smack water hard enough, it can still hurt. If you jump off like a high diving board, it moves out of the way a little bit slower. And then gases are moving really fast. And they're moving all over the place, and so they have the highest amount of energy and they're moving fast. And you can convert between them. If I take a solid piece of ice and put it in a liquid, stir it on up, and it melts, disappears, because I've converted from a solid to a liquid. When you call that, we call it melting. Going from liquids to solids, we call that freezing. We can take a liquid and boil it, right? We call that boiling. And if it's a gas and it goes down to a liquid, we call that condensing. And there's even some cool things that can happen. If you take an ice cube, a little experiment you can do, and put it in your freezer at home and just leave it in the freezer for a long, long time, it will sometimes evaporate down into nothing because the ice will change to a gas without ever going to a liquid. That's called subliming. And it's pretty cool. You can also go that backwards, and I don't remember what it is offhand. So now let's take a look at a really cool demonstration of some states of matter. So now I'm going to take liquid nitrogen. Nitrogen is a gas normally at room temperature. In fact, most of the air around us is nitrogen. So in a way you could call this liquid air, but real air has other things than just nitrogen. But it's very cold. Remember, the colder things go, you go from a gas, gets colder, it gets become a liquid, gets colder, tends to become a solid. So I'm going to pour liquid nitrogen into this little dish here and let it cool off. So I've got the liquid nitrogen in a vacuum bell jar now, and we're going to remove the gases from there. All right? So I'm going to close off all the valves. And remember what happened when we boiled water to make it freeze is that if that liquid nitrogen evaporates, it's going to take energy off, and it's going to make colder, make the nitrogen colder. So we're going to make the nitrogen even colder than normal. Really cold liquid nitrogen. So if you have a liquid and it gets colder, what do you think might happen to it? Well, if we're lucky, it will become a solid, and we will have solid nitrogen. There it is. Boom! Solid nitrogen. There you go. All we need to do, turn off the vacuum, open it up, we could have a nice little nitrogen snow cone. Oh, it all went away. Why did it go away? Well, because when you took away the vacuum, the air rushed back in, that brought in some heat with it and melted it again. So we can turn it off and then turn on the vacuum again and see if we can make more snow. And so there you go. Basically, you've seen liquid air, and now you've seen solid air. Maybe not so much. That was cool.